So now we're going back to property 2 of theorem 2.8, which is properties of inverse matrices. And we have to show that the inverse of a to the k is the inverse of a raised to the kth power. So what we can do is you can use mathematical induction for this because k has to be an integer, a positive integer there. So we can show this for all positive integers k. So proof by mathematical induction. You will remember that we have to first verify a special case. So first we have to verify that the statement holds for k equals to 1, or for the smallest k that the statement makes sense for. So we're going to verify that P1 statement for k equals to 1 is true. So that means a to the first power inverse is equal to a inverse to the first power. Well, a to the first power is just a, so a inverse is equal to anything to the first power is itself. So there's really not, this is immediate. So this means that the statement is true for k equals to 1. So I verified that. So next, the inductive step means that I have to assume that the statement is true for k equals to n, and I have to show that it's true for k equals n plus 1. So what does that mean? What does it mean that the statement is true for k equals n plus 1? That means I have to show that a to the power n plus 1 inverse is equal to a inverse times a inverse dot 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 a inverse this time n plus 1 times, which would be the same as a inverse to the power n plus 1. Right? So we have to show this, and what I have to go off of is that I have to assume that it's that it's true, that the statement is true for the first n factors. So that means what I am assuming to be true is a to the n inverse is equal to a inverse n times, which is a inverse to the power n. Okay, so I have to assume that this is true, and I have to show that this happens then. So we're going to assume, so that's just the scrap work, that's just me trying to figure out what the hypothesis and the conclusion is going to look like. So we're going to assume a to the n inverse is equal to a inverse, which is a inverse to the nth power. So we're assuming this. Now, in order to get from here to here on the right-hand side, all I would have to do is I would multiply the right-hand side here by a inverse. So if I multiplied by a inverse, then the exponent would go up by 1, and I would end up with this. So that's what I'm going to do. So I'm going to multiply both sides by the inverse of a. So that will give me a to the n inverse times the inverse of A. Remember, we have to multiply it. If we multiply it on the right-hand side here, I have to multiply on the right-hand side here. I can't do it on the left there, on the right there. Okay, so this is going to be, well, A to the power -1 to the n times A to the -1. So here, if you multiply by just another one, then you just have, you just went from n to n plus 1. But let's see how that works. Okay. So we have A inverse to the n times A inverse. On the right-hand side here, this is going to end up, this is going to equal A inverse to the power n plus 1. And on the left-hand side, we know the definition, we can use Theorem 2.9. So here we use Theorem 2.9, which says that when you multiply two inverses like that, you can switch the places of the two. So this is the same as A times A to the n, and have the inverse of the product on the outside, right? So this step from here to here is Theorem 2.9. I multiplied by the A on the other side, and my inverse went out there. Okay, so A times A to the n is A to the n plus 1 inverse is equal to, obviously, if you're going to multiply n A inverses by another A inverse, then you get A inverse n plus 1 times, we'll call it n plus 1 factors, same thing. And we showed that on the right-hand side, this is equal to A inverse to the power n plus 1. So then, of course, since we applied induction, we say by the inductive hypothesis, A to the k to the power -1 is equal to k times, which is A inverse to the power k for all positive integers k.
Oh, you couldn't see that. There we go.